Hello everyone, my name is Abhay and I'm part of Data Science and Engineering department at Netflix. Today I'm here to talk about building metric platform using Apache Flink for massive scale. Now this presentation is divided into three major topics. First one is the business use case or the motivation behind building this platform. Second one is the platform design and internal workings. And finally, some of the lessons learned. Now, one might ask, what are the types of metrics that are required? Well, these are the metrics that are used to measure the product performance or the effectiveness of your product out in the world with real users. And these metrics are generally calculated at granularity of a session. Some of the examples might be how many times someone searches when they come to Netflix, how many impressions of titles they see before they pick one title to play, how many times app is crashing on them. And these different metrics tell you how well your product is doing and how happy the users are with your product. As it is evident in this very distracting GIF, once you go to the Netflix, you see lots of different titles presented to you in very different ways. You can browse these titles, you can go and search for some of the content, you can play something, you can change your profile and do so many different things. And these activities are considered user engagement, and these metrics are calculated on top of the data points um, that are considered user engagement. Now, since these metrics are calculated on top of a session, we should also know what are the definitions of these sessions. Well, the short answer is it depends on the use case. For different use cases, these definitions get pretty unique and highly semantic. To give example, the general user engaged session definition would be the user session would start when user starts engaging with Netflix, and it would terminate if user was inactive for a certain number of minutes. Now, this certain number of minutes could be 30 minutes for one data science group, and it could be 15 minutes for other data science group. There is this semantic of playback also. For example, one group might want to consider ongoing playback on the app as active engagement because users are actively viewing that title. But for some other group, they still want to time out the user session if there are no inputs supplied to the app. So, for example, some user is viewing a movie on Netflix for more than 30 minutes and they did not provide any input like volume change or mute or any signal, then they still consider that to be inactivity spanning 30 minutes and they want to terminate the session. Now, some session definitions are based on activities. For example, if somebody changes profile, as in they move from one profile to the other profile, they want to terminate the session when the profile change happens, regardless of inactivity. For search folks, the session would start when somebody searches for a title, and it would end if those search results are abandoned or it results in a playback. Some people want to restrict this session definition only to a part of the product, like between page A and B, and they are not concerned with any other pages. So we have very different definitions based on different data science verticals and how they view user activity. On top of it, we have massive scale. We have more than 167 million members across 190 countries in different time zones. Netflix app is used in millions of different devices like iOS, Android, TV, set-top box, whatnot. They all have very different hardware capabilities and diverse ecosystem of devices. This results in billions of user engagement produced in a day, and the data volume exceeds more than a petabyte. Now, the expectation from the consumer side is that they want these metrics really fast. They want to be able to self-serve. They want flexibility of adding new metrics, and they want quick turnaround time if they want to experiment with metric without spending a lot of efforts. And of course, they don't want to be bothered by this massive scale. Now, to satisfy the requirement of each data science vertical, if there was a supporting engineering org that was building pipelines to satisfy their needs, it is lots of um, different types of efforts in many different groups. And we feel that some sort of horizontal approach or platform approach to solve this problem would ultimately benefit the company better. And it creates a centralized place for someone to come and derive metrics to do product innovation. Now let's talk about the design and inner workings of this platform. So of course, this platform is built on top of Apache Flink, but we have a schema and config registry that also plays very pivotal role in successful operation of this platform. And in Flink, again, we have three major components. The first one is filter. It is similar to the filter operator in a Flink job. It is stateless, it is config driven, and it is in constant communication with the registry to receive updates, and it also performs keybind. Then comes the sessionizer. Now, sessionizer is stateful, and that is the entity that produces all those nuanced and unique session definitions. It is also in constant communication with the registry, and it is made up of all different configurable triggers and process functions. Then we have summarizer. It can be stateful or stateless. If it supports the streaming join, then it becomes stateful, and we use co-process function to achieve that. It is also in constant communication with registry to receive updates. Other than that, it has UDF store just like any other major data crunching framework like Presto or Spark, where UDFs are coded in one module in generic way to be able to receive different types of arguments and ready to be used when called by the summarizer. So let's look at how the platform actually works. Now, the first one is filter. Now, filter is in the line of fire, and it receives those hundreds of billions of events. Now, these are different type of events like play, search, impression, whatnot, and these events can have more than 50 properties in it. But what filter does is it pulls the input schema from the registry, and it trims away all the event properties that are not mentioned in the input schema. It also pulls the configs and kicks out the events that are not useful to the use case. So the final output from this filter is well-defined input schema records, and filter also applies the key by before sending that data to sessionizer. Now comes the sessionizer. Sessionizer collects all these input schema records into RocksDB state and triggers within sessionizer which receive all those configs, decide when a session is ready to be flushed. When a session is flushed, the process function receives those sessions, and it pulls the session schema from the registry and converts the array of these input records into session schema. Now, generally, the way it works is that, for example, if your session was made up of 50 events, then you have an array of 50 input record schemas. Now, some attributes are common across all 50 events. You would put them at the top level. So fields like account would become part of the top level properties. And there are other properties which can take up more than one values, like what type of events are there, what was the timestamp on those events, what page did it fire from. All these properties which can take up more than one value will be part of an array. So the final output is a nice bag of a session that is supplied to the summarizer. Now, summarizer has a special schema that it pulls from the registry. In addition to those keys and their types, it also has the function signature which derives that type. And the argument in that function signature is any value that is part of the sessionizer schema. So for example, if you want to know how many pages somebody visited in a session, then page will become the input of distinct count UDF, and it will produce the page visited matrix. So the final output of summarizer is a flattened record, which consists of different dimensions like account, device, operating system, and lots of metrics and or measurements, which consumers find very useful. Uh, and it is essentially gold mine for consumers because they can slice and dice these measurements across different dimensions to be used. Now, the core requirement of this platform was ability to add a new metric pretty fast. How do we do that? Well, plain old schema evolution drives the output of the platform. So adding a new metric is just a matter of registering new fields to the schema and specifying what functions to apply. So let's say now we want to calculate a new metric, like how many titles were seen by somebody in this session. So what we'll do is we'll just add the title field in the input schema. Now, of course, it has to come in the payload of input events. And the schema, input schema will evolve to a newer version, ID2. Similarly, for session schema, it will evolve to version ID2 and it will involve all those titles seen in a session as part of the array. And we add that function in the summarizer schema, which also now have evolved to ID2 to add that metric. And if there was any other field that was already present, then that also can be part of a new UDF that you just add into the summarizer schema. So this way, you just update the schema in registry, and those updates are pushed to filter, sessionizer, and summarizer. And without redeploying jobs, after this schema update, from that point onwards, you have new metrics flowing in your data stream, which which provides for the very quick turnaround time and without any redeployments. And in some cases where the requirement for metric is very complicated and that UDF is not present in the store, at that time, the only effort would be to code and test that UDF and add it to the UDF store. Now let's talk about the streaming join use case. It is pretty similar. It will just add a new filter component for that second stream. And usually the streaming join is made possible in this platform at summarizer level because all those multi-billion events are converted into compact session bags uh, in less than billions of those sessions. And summarizer is smart enough to adjust these elements from the second stream into the session bag so that we could also drive it from the schema and calculate new metric. So all of this adds to the velocity of product innovation because new metrics can be derived pretty fast and people can add new metrics with a greater velocity. Now let's talk about some of the lessons learned. The first one is, hey, break the monolith into simpler reusable components, which means filter, sessionizer, summarizer could be independent jobs in their own right. We actually tried with the monolith where all these components were part of one job, and we quickly realized that checkpoints weren't going through and job wasn't stable at all. And streaming join also created for an interesting back pressure dynamic. So job was constantly going in restart loops and it was replaying data again and again, resulting in poor data quality. So breaking the job down where filter and sessionizer was one job and summarizer was other helped us control the state size, and thus overall it was more stable in regards of stability, checkpoint, and operations. And this means that all the sessions were also breaking properly within the job, and data quality was good. Now, this also allowed us for reusability. For example, downstream of one sessionizer, you can have multiple summarizers that are serving different teams. One could have streaming join, other could not. And if there are disruptions in one summarizer, at least the data set coming out of other summarizer for a different team is protected and isolated. So their data set is not impacted. The other lesson was that we used ingestion time to drive the watermark instead of event time, because all this data comes from very diverse set of devices with different hardware capabilities and hardware clocks. So event time wasn't that reliable. Even after our own attempts to augment the event time, there were lots of fluctuations in watermark because of this unreliable event time. We also have almost more than 20% of the data arriving late simply because it was flushed late from the client, and that also resulted in like not predictable watermark, which resulted in sessions being broken unpredictably, which means the metrics calculated on those sessions were not reliable. Now, at any given point, we have sizable amount of data being ingested, and that ingestion time is immutable whenever it is stored in a message bus. So if your job was down for more than an hour, and if you wanted to replay all that data really fast, you could beef up your cluster and consume all that data with a faster rate, and your watermark would still increment smoothly. Now, another effect of this was that we had to take care of ordering of events in Sessionizer. So basically, whether the timestamps are messed up or they are arriving late or out of order, we handle all of that after the fact. All those events were stored in RocksDB, and then we started processing it. And we also have lots of other attributes that help us with ordering events in addition to timestamp. Now, initially, when we developed this job, our Kafka consumer would give us a hash map of string keys and object values representing the events. And we naively used it, and we then realized that replacing it with a compacted array drastically reduces your state size. So our checkpoint size, here is a parallel comparison of two jobs using different formats. So the one that uses hashmap produced 1.5 terabytes of checkpoint sizes, and the one using array was somewhere around zero point 0.5 terabytes. And this was very interesting lesson because this gave us a headway to grow more. And because the checkpoint state was less CPU was consumed there, and it ultimately resulted in better job stability. Now, when we moved it to Avro, once we had Avro support, the binary Avro serialization further drove down the state size by 30%. So from 520 gigabytes to 340 gigabytes. Again, these are two jobs running in parallel with different mechanisms of serialization. And as you can see that we have a noticeable gain in the state size. So doing all these optimizations helped with our state size. So even if we needed to redeploy the job from a save point, the size of save point itself wasn't that huge, and we were able to restart our job from a save point too, ensuring the proper data quality after any redeployments. So these are some of the lessons learned. Ultimately, we want the Flink job to be stable and be able to checkpoint properly so that if we have to redeploy from previous save point or checkpoint, the data quality is not compromised and there are not many restarts affecting the data quality. So these are some of the lessons we learned. Ultimately, the biggest lesson is that data quality is the king. No matter how good of a framework you build, if it is not producing the proper data quality, then nobody's going to use it. So this is all I had to share today. I hope you found it useful, and thank you so much for listening. I am around for any questions.